Section 5.1 is angles and their measure. We're transitioning away from the algebra into the trigonometry part of the course. When you take calculus, the hardest part about calculus is the algebra involved, and then typically people come in fairly weak in trig for some reason. It looks like most of you guys have at least some sort of trig in your background, so this may be an easier section for you, but easy does not mean back off of doing the homework and the quizzes and such that I post, because that practice is what keeps it fresh and makes it easy, and you want the course to seem easy. So starting now at the beginning, we're going to be looking at angles and their measures. These are the objectives that we hope to have mastered by the end of this section. We're going to be converting between degrees and decimals, degree, minute, second measures, and all that good stuff, and finding the arc length, and you guys can read that. So we're going to start out with first, what is a ray? Because when we make angles, the first component is a ray. This initial point we call right here the vertex, and then it's going off in some direction. We create angles then by combining two rays that intersect at a point called the vertex. The initial side typically will be the positive x-axis, and then we go around until we intersect the terminal side. So this would be read as angle alpha because that Greek letter there is alpha. A positive angle is measured in a counterclockwise direction. If we measure in a clockwise direction, we end up with a negative angle. This angle measure is now beta. The measure of angle beta has the same initial and terminal side as that of alpha, even though they look like they're the same angle. They're different because one is measured in a positive direction, one is measured in a negative direction. Angle gamma here goes all the way around 360 degrees, one revolution around, and then picks up. And all three of these angles have the same initial side and terminal side, but they're actually three different measures of angles. And we need to get comfortable with that concept that we can have the same initial and terminal side, and yet we can have different angles. This is a counterclockwise direction, which means that it's a positive rotation, but it goes around through one revolution. A revolution is one time around the circle, or 360 degrees. All right, right here then we see we have an angle in standard position. It's called standard position whenever the initial side is on the positive x-axis and the terminal side is not. This is an angle theta, where theta terminates in quadrant 2. The quadrants of the angles are 1, 2, 3, and 4, and we will refer to these angles by the quadrant of the terminal side. Here's an angle that terminates in quadrant 2. Here's an angle that terminates in quadrant 3. This angle right here is positive because it moves in a counterclockwise direction. This angle is negative because it moves in a clockwise direction. Once again, you can check the quadrants. Now, if your angle terminates on one of the axes, we call this a quadrant angle. And the quadrant angles are special angles to us because we can easily plot points that lie on the terminal side of the angles. There's two ways of measuring angles. We have degrees and we have radians. First, we're going to look at degrees. One revolution through is a counterclockwise direction is 360 degrees. So if you're out doing 360s in your truck or whatever, that means you're going in circles. We take a fourth of the circle and we end up getting 90 degrees. So if we're looking at an XY axis here, and this measures 360 degrees all the way around, we see that we can go halfway, and that's going to put us at half of 360, or 180 degrees. Halfway between 0 and 360, by the way, are what we call coterminal angles. That means they stop at the same point. The terminal side would be the same. If we go halfway between 0 and 180, that puts us at 90 degrees, and then halfway between 180 and 360 is 270 degrees. So this is the measure of our quadrant angles, and that's something that I expect you have memorized. Drawing an angle. If I ask you to draw a 45-degree angle, I would hope that you could do that. 45 is half of what? It's half of 90, so what we could do is plug in our positive x and y axis here, and then we end up with an angle that bisects that, and we would call this angle right here 45 degrees. What about negative 90? What would that be coterminal to? 270. So negative 90 degrees would be this angle right here. And then 225 degrees. If we draw an angle that measures 225 degrees, we know there was going to be more than 180, right? And 180 plus 45 happens to be 225 degrees. And then 405 degrees. What can you tell me about this angle? It goes completely around. 360 from 405 is what? 45. So this is going to stop right here in quadrant 1. But when I look at the measure, it's going to go all the way around and then stop right here. And how we got that was we said 405 minus 360 is 45 degrees. Because the first revolution here is at 360 when we stop right here. That's one revolution, so we can take it off. And then we add 45 degrees to that, and that means that this is going to be coterminal to this angle right here that measures 45 degrees. Converting between decimals and degrees, minutes, and seconds. You guys have a button on your calculator that will do this for you, but let's talk about minutes and seconds because you may not have spent a lot of time with this, and I don't know where you're going to be going after this class. I want to be preparing you for any possible outcome, and you may need to know what degrees, minutes, and seconds are. Well, there's 360 degrees in one revolution of a circle, and 1 degree is equal to 60 minutes. This little tick mark right here is what we use for minutes. And just like there's 60 seconds in a minute in time, there's 60 seconds in a minute in angle measure. It's just a way to refine how accurately we measure our angles. In this problem right here, we're going to be looking at converting between degrees, minutes, seconds, and decimal form. So we want to convert 45 degrees, 10 minutes, and 15 seconds to decimal degrees. You can do this by hand or you can do it by your calculator, and I'm quite frankly fine with you guys using your calculator. So if you will look at this part right here, right above the apps key on your calculator, it says angle, right? So we are going to use that feature to put in the degrees, minutes, and seconds. First of all, actually on this it doesn't matter if your calculator's in degree or radians, but it's always good to check your mode. Since we're dealing with degrees, I'm going to go ahead and change my calculator to degrees out of radians. And then I'm going to type in 45 degrees. So we hit second angle, and that gives us the degrees. And then we have 10 minutes, so we hit back into angle, and that's 2. And then we need to put in 15 seconds. So that would be 15, and the only place that I've found seconds listed actually is in the catalog. So if you hit second catalog and go up, seconds is not too far away. I don't know why it's not on the angle. And then if you hit enter, it will convert this to decimal degrees. And in this problem, we're asked to round to 4 decimal places. So when we round this to 4 decimal places, what would we write down for our answer? It's 45.1708 degrees. In the next problem, we're asked to convert decimal degrees to degrees, minutes, and seconds. And this is even easier on the calculator. Pull up your calculator. Let me clear this off. And we have 21.256. Go back into angle. And this is degrees. And we're going to convert this to, so go back into angle, degrees, minutes, and seconds. And that's number 4, where we convert the previous, or the answer to degrees, minutes, seconds. And it gives it to us 21 degrees, 15 minutes, and 21.6 seconds. Make sure that your calculator's in the right mode for the problem. And we're going to round to the nearest second. So what would we have written for our answer here? 21 degrees, 15 minutes, 22 seconds. You'll have an opportunity to practice some of these on your homework. Just not too terribly many. It's just a minor skill that you need to work on. All right, next, find the length of an arc of a circle. Okay, in order to find lengths of arcs of circles, it's easier actually to work with a radian. So an arc here would be this distance right here. The region on a circle that's trapped between the initial side and the terminal side of an angle that passes through some central angle. Now, if the radius, if we're looking at 1 radian, where this angle right here measures 1 radian, this is how we define a radian, by the way, or it's the angle that would give us an arc length that's equal to the radius. So it doesn't matter what the radius is. If your angle measures 1 radian, then if we have a circle of radius 1, the arc length is going to be 1. If we have a circle of radius 3, the length of the arc here would be 3. Because the central angle here measures 1 radian, there's a ratio or proportion between those those measures for the radius and the arc length. That's how we come up with it. So the definition of a radian is it's an angle with its vertex at the center of a circle that intercepts an arc on the circle equal in length to the radius of the circle. That's an angle, or that has a measure of 1 radian. We can measure circles in degrees, or we can measure circles in radians, or measure angles, not just circles. Now, it's in a lot of applications that we do in physics and engineering and calculus, we would prefer the angle to be measured in radians, because a radian is a unitless measure. It's just a number. It's a ratio between the radius of the circle and the arc length that the angle cuts out. So we would prefer things to be measured in radians. Well, let's look at our circle right fast that we had just looked at in degrees. And we said that this circle right here, if we look at the measure on this first quadrant angle, we said that this was either 0 degrees or 360 degrees, right? And then we went around to what measure? 90, 180, and 270. Now, an arc length, if we go all the way around the circle, what is the distance around a circle called? Circumference. And we have a formula for calculating the circumference of a circle, don't we? The circumference is equal to 2 pi r, right? So if we have a circle with the radius is 1, what will that circumference be if we go all the way around the circle? 2 pi, right? So if we go all the way around a circle that measures 300, or an angle that measures 360 degrees would be equivalent to an angle of 2 pi radians. Would you agree with that? And if we cut out an angle that measured, say, 180 degrees, if we have this angle right here, it measures 180 degrees, but how many radians would that measure? Just pi. It would be half of that 2 pi. And if we went halfway between 0 and 0 and pi, what would we get? 90 degrees would be equivalent to what in terms of pi? It's half a pi, because we're halfway between 0 and pi. Does that make sense? So there's 0 radians, pi over 2 radians, pi radians. The next one is going to be 3 pi over 2 radians, and then finally 2 pi radians. Does that make sense? How we end up with this radian measure that's equivalent to this given degree measure. Now that's going to help us when it comes to finding arc lengths and working with angles measured in radians. In calculus, we only work with angles that are measured in radians. So we're going to have to learn how to quit thinking in degrees, which is natural because that's what we learned in high school, and start thinking in radians. And I'm hoping that throughout the rest of this course, you guys will become fluent in radian, where you'll start thinking in radians as opposed to degrees. All right, so we have a theorem for arc length. It says for a circle of radius r, a central angle of theta radians subtends an arc whose length is s. So this theorem we can use then, and this is kind of what the picture showed. The arc length is equal to r times theta, where theta is measured in radians. That was the circle that I illustrated, where theta was equal to 1. We said the arc length was equal to the radius. Well, we can use this theorem now to figure out how to come up with a radian measure. That angle theta, if I solved this equation for theta, I would get s over r, where s is the arc length and r is the radius. So what we see is an angle measured in radians is just a ratio between the arc length and the radius of the circle. That's a simplified way to think about what an angle measured in radians is. It's just a ratio between the arc length and the radius of the circle. We can use that now to find the length of an arc in this example problem. It says find the length of the arc of a circle of radius 4 meters subtended by a central angle of 0.5 radians. All right, so we go to the formula, s equals r theta. We're looking for the arc length. This, by the way, I expect you to know. I don't want you to just memorize things. I want you to understand the reasoning behind them. Because if you understand the reasoning, if you forget a formula, you can develop it then later on your own. The arc length is just the angle measured in radians times the length of the radius. So this is going to be s equals r theta. Well, if you can remember that theta is just a ratio of the arc length to the radius of the circle, you can solve that equation to get this. All right, so in this formula, or in this problem, what is r going to be? 4. And what is the angle measured in radians? 0.5, and this is equal to then to what? You look at the problem to see what the unit of measure was. Next, we want to practice converting from degrees to radians and radians to degrees. We said that the circumference of a circle was 2 pi r. Let's let our radius be 1. That makes life easy. We would say then that 360 degrees, that's the measure for the central angle of an arc that measures a whole circle. That's equal to what in radians? 2 pi if the radius is 1. So we need a way to come up with a conversion factor. So what we can do here is divide both sides by 2, and we end up with 180 degrees measures pi radians. We don't typically put a number here or a value here, but you can if you want. This would be pi radians. So we can use this because these two values are equal. We're going to use something called dimensional analysis because pi over 180 degrees is equal to 180 degrees over pi radians, right? These two things are equal because the numerator and the denominator are equal in value, and those two things put over each other equals 1. So if we multiply something by 1, we don't change the value of that thing, but we can cancel out the units. So right here, if I have 180 degrees and I want to convert that to radians, I set up my problem so that I have my 80 degrees. I'm going to make this a fraction. I have my 80 degrees on top. Now I want to multiply this by something so that the degrees will cancel out and I'm left with radians. Well, what can I multiply by so that the degrees cancels out and the radians are left on top? Pi over 180. Because now the degrees are going to cancel and I'm left with 80 divided by 180. You can do this on your calculator so you can get nice fractions. We hit math, enter, and it'll convert this number to a fraction for us. We get 4 pi over 9. Or you could say 4/9 pi. It's the same thing. It'd be 80 pi divided by 180 reduces to 4 pi over 9. What do we do here? Same thing, right? We start out with 140 degrees. We multiply it by what? We want radians. We're getting rid of the degrees. We're canceling out the degrees. So this ends up being 140 pi over 180. But that will reduce to what? What about negative angles? Doesn't matter. We just set it up with the negative in the problem. So this would be negative 30 degrees times pi over 180. And I typically put this over 1 so it makes it easier to see that we're looking at negative 30 pi over 180. And that will reduce to negative pi over 6. And then we do the same thing for 100 degrees. We're going to multiply it by pi over 180. And we end up with, this reduces to, like you said, 5 pi over 9. If you forget what to multiply by, go back to your circle and remember that 180 degrees is equal to pi radians, and you just set up a ratio between 180 and pi. What if we're asked to go the other direction, convert from radians to degrees? Well, we start here with 2 pi over 3 radians, and we're going to multiply this by what? I want the radians to cancel. Radians are going to be on bottom, and I'm going to be left with 180 degrees. So that's going to be equal to, is that 120? 120 degrees. And then we have 5 pi over 6. We're going to multiply this by 180 over pi. Pi's are going to cancel out. 6 goes into 183 times. 3 times 5 is 150 degrees then. And then I just don't feel a strong need to do the rest of these. You guys got it, right? Now we need to look at an application. What can we do with all of this radian stuff? One of the practical applications has to do with measuring things that are on a grand scale, such as the Earth, finding the distance between two cities. In this figure, we see how we can use the center of the Earth and a line from the center of the Earth to an equator, along with this angle here that measures a line of latitude. If we find out what that angle is from the equator up to a particular line of latitude, and we know the radius of the Earth is 3,960 miles. We can use that information then to find the length. Because of the curvature of the Earth, we can't just draw a straight line. We can use the arc length formula, S equals R theta, in order to find the distance between 2 points on the globe, as long as they line up north to south. So right here, in this problem, we're told that Glasgow, Montana is due north of Albuquerque. So they're on the same line of longitude. These lines right here on the globe are called lines of longitude, taking you back to your geography days, right? Glasgow, Montana is due north of Albuquerque, New Mexico. Find the distance between Glasgow, and they give us the angle measure for the line of latitude, and Albuquerque, which is at 35 degrees 5 minutes north latitude. Assume that the radius of the Earth is 3,960 miles. What we need to do then is find out what is this central angle right here, and how would we determine that central angle? Theta is going to be equal to the angle between, right here, the central angle that's subtended on the globe. Well, the furthest one north is Glasgow, Montana, and that's 48 degrees 9 minutes. And we subtract from that this 35 degrees 5 minutes, and that gives us the measure of this central angle, does it not? This measure right here on this line of latitude is the measure north of the equator. So right here would be 0 degrees. And then as we move north, we get our angle right here, this angle theta. So Glasgow measures 48 degrees 9 minutes north of the equator. Albuquerque is 35 degrees 5 minutes north. The angle between those two cities would be the difference between these two angles. And what do we get for theta then? This is why God gave us calculators. And what we're looking for then is the arc length right here. And the formula for arc length is S equals R theta. We know a number we can plug in for R. We know an angle measured in degrees for theta, but what do we have to convert that angle measure to? This formula only works if the angle is measured in radians. The information you're given here on the angle is degrees. So your first step right here is to convert theta to radians. That's got to be your first step in order for this to work. Well, I'm going to build that conversion process into my formula. So I have S equals R theta. The radius we're told is 3,960 miles times 13 degrees 4 minutes times. Now how do I convert this unit to radians? 180 degrees is pi radians. So on my calculator, first of all, convert 13 degrees 4 minutes to decimal degrees. 13.06. You know what? I'm going to leave it in degrees, minutes, and seconds. So I'm going to store this value as alpha A for angle. So on my calculator, I'm going to type in 3,960 times alpha A, because that's the stored value, times pi divided by 180. And we end up with 903 miles. We're going to round this to the nearest mile. I know my units are miles because the units here canceled each other out. Radians have no units, and then the only other units here are miles. That's called dimensional analysis, is when you let your units kind of drive how you cancel things out. I will expect that you can do this on your own. All right, finding the area of a sector of a circle. We want to find the area of a sector of a circle as a function of theta. If we were, or a sector as opposed to a whole circle. If we were looking at the entire circle, what is the formula for the area of a circle? Okay, so if we just wanted a piece of the circle, say this area of this sector, I can look at it as a proportion or set up a proportion to the area of a circle. I would have the area of this sector in relation to this angle theta is equal to the area of the entire circle in relation to the central angle for an entire circle. Do you see how I set up this ratio? Looking at the sector, just the sector. There's the area of the sector and the angle theta. If I look at the entire circle, there's the area of the entire circle, and we know that it's pi r squared. And we know the angle that cuts out the entire circle is 2 pi radians. So now we can cross multiply this and solve for A, and we're going to get 2 pi times A equals pi r squared theta. Now what would I do to solve for A? Divide both sides by 2 pi. When I divide by 2 pi, I end up with A, the area of a sector, is equal to 1/2 r squared theta. Because the pi's are going to cancel out, the 2's still in the denominator, so I'm just going to pull it out front. And if you want to write it r squared theta over 2, you can, but that's the same thing as 1/2 r squared theta, which is how we actually write the formula for the area of a sector. But this is how you develop it. In case you forget the formula, you just set up a proportion between the area of a sector and the area of a circle. As long as you know that a circle has a central angle of 2 pi radians. We can now use this formula that we created to find the area of a sector of a circle of radius 5 feet formed by an angle of 40 degrees. Round the answer to 2 decimal places. So we're going to use A equals 1/2 times the radius squared times our central angle theta. But theta has to be measured in. Why does it have to be measured in radians? Because I used a 2 pi here instead of a 360 degrees. If I used my angles measured in radians to create the formula, I can only work with angles measured in radians. So this 40 degrees I can convert to radians by multiplying it by what? Pi over 180. So that's going to give us 25 halves times, what will this reduce to? 40 over 180 is 4 over 18. 2 pi over what? 9. So the 2's are going to cancel out and we get 25 pi over 9. And then we put this into our calculators in order to get a decimal approximation. So this is going to be 25 pi. And use the pi button on your calculator, not 3.14. And rounded to 2 decimal places, we're going to get 8.73. 8.73 what? Feet. Because this, no, it's not feet. It's square feet. Because right here, the 5 was measured in feet, but then I squared it, and feet squared is square feet. The degrees are going to cancel out, so I'm not worried about that. The units of this are going to be square feet. Number 5, finding the linear speed of an object traveling in circular motion. Speed is the distance you cover over a given amount of time, right? So S is our arc length, T is our time, V is velocity, which we call speed. So velocity is equal to distance divided by time. This is the linear speed. It's how fast, if you're an object on the outside of this circle, it's how fast is that object traveling. So that's linear speed. Angular speed is how fast you're rotating. It's how fast is the angle inside changing. So angular speed, we use omega. That's this. You're going to learn a little Greek in this class. Okay. This is a lowercase omega. Omega is equal to theta divided by t. It's our angular speed, so it's the amount of the angle that we cover divided by time. Now, if we take these two formulas and put them together, we end up with our linear speed is equal, linear velocity is equal to r omega. Well, how do I get that? S is equal to r theta, isn't it? V is equal to S over t, but S we said is r theta. Arc length is the radius times the angle that it's the arc length subtended by the angle theta. Well, that's just r times omega over t, theta over t, isn't it? And that's where we get the r omega from. So if you know linear speed, distance divided by time, and angular speed, angle divided by time, you can end up with this formula. Velocity is equal to the radius times the angular velocity. Now let me see if I can explain or give you a context in which you can understand the difference between angular velocity and linear velocity. You guys ever go to the skating rink and hold hands and you play whip? You know what I'm talking about? The person on the end is going super, super, super fast as the person at the inside starts rotating and everybody starts holding hands and slinging out. The person at the inside or at the pivot point, if you got a line that's marching in the band and you want that whole line to turn in a straight line, this person's just basically standing still and rotating, right? They're not going very fast. How they're moving is the angular velocity. But the person on the end has to double time it to keep everything going. Or if you're at the skating rink, they're the ones that go flying off into the wall, right? That's the linear velocity, the speed of the person on the outside, as opposed to the angular velocity, that person that's just rotating. Now, we can use these formulas to find linear speeds. It says a child is spinning a rock at the end of a 2-foot rope at a rate of 200 revolutions per minute. Find the linear speed of the rock when it is released. So 200 revolutions per minute. That kid's really flinging that rock, right? All right, so we want to know the linear speed of the rock when it's released. So we start with what we're given. We're given 200 revolutions in 1 minute. And we're going to use dimensional analysis to help us here. We know that the radius is going to be the length of the rope, and the formula for linear speed is going to be equal to r omega. It's the length of the radius times the angular velocity. This bit right here is our velocity, our angular velocity, 200 revolutions per minute. In place of r, we're going to plug in 2 feet. So we have 2 feet, and I'm using the units here, times omega, which is 200 revolutions per 1 minute. We got to convert this to radians. So 1 revolution is equal to how many radians? 2 pi radians, right? And our angle has to be measured in radians, not revolutions. So this ends up being, when we multiply here, our units are going to cancel out here, and our speed is going to be measured in feet per minute. So that's going to be 2 times 200 times 2 pi. That's going to be 800 pi. What are the units going to be? Feet per minute. Feet per minute doesn't mean a whole lot to me, but miles per hour does. Can we convert this to miles per hour? Sure we can. So this is 800 pi feet per 1 minute. And I want to convert the feet to miles. So feet are going to go on bottom. And there's 5,280 feet in 1 mile. And I want minutes to go to hours. So there's how many minutes in an hour? 60 minutes in 1 hour. So when I multiply across the top, I get 8 times 6 is 48, 1,000 pi divided by 5,280. And my units are going to be measured in what? So somebody do this on the calculator for me. 48,000 pi divided by 5,280. It's 48,000 pi divided by 5,280. 28.6, we'll say. And the units here, feet canceled with feet, leaving behind miles. Oh, this MI should be MIN for minute. Minutes canceled with minutes, leaving behind hours. So we have miles per hour. This is why your mom said don't do that. Don't fling the yo-yo around over your head in the house, because it can get up some velocity. We didn't even account for the mass of the rock here. You know, when it leaves, what kind of force is it going to hit you with? But we'll leave that for the physics teacher. It's still an interesting question. It's enough to conk somebody on the head pretty good, or bust a TV or a lamp.